Thanks for the introduction, David, and it's a pleasure to be here. I just want to get some feel into the kind of language we should use. How many are statisticians? About 35%. Computer scientists? Oh, 55. And the rest are, I guess, in the fields that are statistically minded. I assume, like.
I might actually just a remark about at the end of the talk, the question and answer. But for those of you who'd like to kind of have a more in-depth conversation, Judea will be here for a while. We can chat here, or there's a room 520 Mud is available if a group wants to go there and have a more intimate chat. So,
okay. You want me to speak louder?
Do you want me to turn the light up here?
Go ahead and do what needs to be done. I'm here to serve. Okay, so we are going to talk about cause and effect. My title says Mathematics of Cause and Effect. In this way, I have protected myself against all criticism in the form of how do you get these assumptions? Because mathematics goes from assumptions to conclusions. By saying mathematics, I'm only going to lead you from assumptions to conclusions, and I'm not responsible for the veracity of the assumptions. So that way, I'm sure I've cut down 99% of your question. I feel secure now. And I'll talk first about the causal evolution. Excuse my dramatic vocabulary. It has been a revolution. And I can back it up by simply counting the number of papers in a conference such as JSM, the Joint Statistical Meeting, which is a major conference for statisticians. If in 2003, 10 years ago, there were about 11 papers with a title that has to do with causality, or causation. This year it's over 130. Okay. But that doesn't, it's only dry numbers. What counts is the attitude of the authors. Whereas in 2003, causality was a liability, always followed with apologies. I don't really mean, but I mean, but it was. Today, you find titles in the form of causally sound approach to XYZ, or causally defined. Oh, I hope it's okay. Oh, thank you, Kathy. I put it in my pocket. I think it's the best way. So causality became something to be proud of. I'm doing something right. I'm doing something respectable. Where did this aura of respectability came from? And I attribute it to a whole change of paradigm. Okay? Whereas prior to 2000, we had the idea of association to be the oracle of all thinking. Today we are thinking about something deeper, causal or counterfactual, namely reality. So reality got a face in statistics proper, which is a revolution. Because if you take any book in statistics, any undergraduate or graduate, you find that reality does not have a face there. I'll explain what I mean by that. They talk about data like this institute, right? It's for data, not for reality, which makes the data. So it's really a contradiction here that I would like you to think about. And I I compare it to the revolution that took place in the ancient world between the Babylonian science and the Greek science. The Babylonians were much ahead of the Greeks in terms of predicting astronomical phenomena. They could predict the cycle of Venus, the moon, the time that the moon will appear and be full, and so on, much better than the Greek. The Greek had a totally metaphorical science. We are walking on a turtle shell, and the sky, the stars that you see are not really bodies. They are holes poked in an opaque shell through which we see the celestial light or the eternal light. Okay? So it was totally wrong. It was built on metaphors. What does it mean, metaphors? Metaphors mean analogies to phenomena that we are expert in, namely turtles. Yeah, we understand how turtle walks and what it means. So the analogy to a familiar phenomena in everyday life, that made Greek science, and who do you think won in this contest? It's a Greek science that won, and not the Babylonian. They predicted celestial phenomena by time series extrapolation. Not exactly Fourier, but almost polynomial extrapolation, okay? And they were expert in that. But who do you think was the first who measured the radius of the Earth? It was Eratosthenes. It was a Greek 200 BC who lived near Alexandria, and he made two assumptions that for which he had no support. One, that the sun is very far away, and the other is that we live in a turtle shell, so it must have some radius, right? So put in the two together, you find the difference in the angle between the shadows in Alexandria and the shadows in Cyrene next to the Aswan Dam, and you compare the two angles, and you know the distance between the two locations, chick-chack, and you compute the radius of the Earth, very close to what it is, what we have today. Amazing phenomenon, something that would not occur to a Babylonian astronomer. Then I'll talk about the two fundamental laws of causal inference, which means you can take just two sentences and walk out of this room and you can derive everything by yourself. Everything that I'm going to say is just going to be logical exercise from these two principles. And then I'll show some applications. Application of counterfactual analysis to problem solving, problems that really have been bothering people for a long time. One is policy evaluation. The other one is mediation. What's the difference between, how does effect propagates from one cause to the effect? What are the paths? The difference between direct effect and indirect effect. It's scientifically important and also practically important. And how do you generalize from the laboratory to the field? It's a problem that constantly bothers the philosophers. Scientists just have the understanding that if you conduct experiments on monkeys, some of them will apply to human beings, but others will not, okay? And they understand it, but further analysis of that jump from the laboratory to the field is needed. And I'll show you how it can be, how it follows from the two principles of causal reasoning. And the third one is just something that we happen to do lately. Here's an example of a problem that has been treated in statistics as a statistical problem. You have a missing data. What could be more statistical than that? Well, it turns out that if you look at it from a causal perspective and you ask yourself, what is the mechanism behind the missingness? And you represent it as a causal graph, the same way that we ask, how do you advise policymakers? Okay. Then you get insights, new insights, that were not obtained by the crude statistical analysis. And other, I will not have a time, I know that I wouldn't have time to discuss, question of heterogeneity. How do you know if you have some strange idiosyncratic group of people which have no names but are extremely allergic to some drug that you are evaluating? How do you discover that in a population data? Okay. Selection bias, attributions. Okay. I'm ready to continue into the causal revolution by giving you starting with a caricature of what statistics or data analysis is until now. Behind the curtain, we assume that there is a joint distribution of the variables which we observe. That's the P. I sometimes call it an oracle. I call it Santa Claus, because no one has ever seen one, but we approximate it, or we assume we approximate it, and we even have theorems of degree approximation to it using the hypothesis that it exists. Okay. That was a Bernoulli invention. If you assume the coin is loaded with P, right, then I can tell you how close you are to P. All this nice exercise, very extremely intellectually rich. And the whole literature on statistics, fills libraries, shelves and shelves and shelves. It's because the Q, the property, the aspect of P that you are trying to estimate can be extremely complex, especially in dynamics, time series, and so on. But this is what statistics is about. Nature, or P, not nature, P spits out data. We look at the data and we want to find to estimate some property of P, for instance, estimate the mean, or estimate the conditional probability that a person who bought product A will buy product B. And I know many of us are doing, or maybe not me, but many of you probably are making good money for working for Google just for this purpose. So this is a data analysis paradigm. And causality requires that we make a tiny jump, because we are asking questions of a different nature. We are asking for a change in P into P prime. For instance, a sales manager wakes up one morning and estimate the probability of sales if we double the price. Out of whimsical decision to double the price of our product. Okay? So you have a new probability. P prime, I call it. And the question is, how does P change into P prime? Notice that you are not asking for properties of P anymore. You are asking for the sales after the intervention, after we double the price. So you're asking for properties of P prime. So now we need a new oracle that will do two things for us. One is will tell us how P prime it can be constructed from P, and how we compute or estimate the aspects of P prime. Okay? For instance, estimate the probability of cancer if we ban smoking today. Okay? Smoking has never been banned successfully in any culture, but we are just doing hypothetical experiments or hypothetical change in the behavior of people, and trying to stipulate what will be the behavior after that, in turn, what will be the cancerous or effect on the biology and cancer-producing agents once we successfully produce this change. So it's a whole new game. Some statisticians do not believe that this is a change, because we can express everything in terms of P if you just enlarge the vocabulary of your variables. Okay? But I prefer to look at it as a change. It's much more natural, I think, and I'll prove it to you later on when we compare the two aspects. Okay, and there's another. First of all, I will convince you that you cannot compute P prime from P. because it's not like conditioning on the price double. See, the probability of sales after the intervention is not equal to sales given the intervention, because seeing that something happened, the price double, is different than doubling it, than making it happen. Like seeing that the rooster crowed predicts the sunrise, but making the rooster crow in the middle of the night will not make the sunrise. Now I convinced you. Roosters are extremely useful in the So doing and seeing are two different things. And it so happens that probability has endowed us with an operation for seeing, operator, this Bayes conditioning bar that we are all in love with, because it's very powerful, is really expresses the act of seeing. If I see that you have certain symptoms, then I can infer what kind of disease you have, or the other way around. Okay? So this is what the change of belief due to observations, due to evidence. It's all taken care of by the Bayesian conditioning bar. But now we have a different operator, do, okay? Double the price. Probability has been not been graceful to us, did not equip us with an operator for doing. It's something that needs to be, we have to cope with. It's something we have to resign to. It's very painful to resign to the idea that the language in which we grew up, in probability theory, a language with which we built all our profession, in which we invested all our career, cannot give us the answer to a very simple thing, double the price. It's a traumatic experience. I'm telling you, I've 20 years fighting this trauma with good colleagues, good scientists who keep on telling me, but it must be within the paradigm of statistics, it must be part of probability theory. Are you inventing a new probability theory? So what is the definition? Well, for computer scientists, it's very easy transition, because we are changing languages every day. Whenever Microsoft comes out with a new version, for statistician, it's a war of attrition. Anyhow, here it is. P does not tell us how it ought to change. Bayesian conditioning, the evidence, the probability theory, tell us how it's going to change as a result of new observations. That's the whole idea of conditioning bar. You give me P, then you tell me, no, but I observed that he suffers from schizophrenia. Wow, then I condition on schizophrenia. Now I have a new P. So you see how powerful probability is? It not only tells you about what your belief should be today, it also tells you what your belief should be tomorrow if you observe schizophrenia. But it doesn't tell you how it's going to change as a result of external intervention. For this you need another oracle. So we go here and we say, excuse me, before we go to new oracle, I want something more from the oracle. I also would like the oracle to answer questions of counterfactual nature. For instance, what if we were to double the price? So here we are talking about a particular customer named Joe, okay? He estimated the probability that the customer who bought A would still buy A if we were to double the price. So you're talking about one individual, not a population anymore. Okay? And you want an answer to that, because this is the kind of questions we ask in everyday life. This is the question that we communicate with, and I wouldn't have time, but I'll convince you that scientists communicate through the language of counterfactual. Okay? F is equal to ma is a counterfactual statement that says if the force were to double, then the acceleration will double, or would double. But I'll talk about this very object. I have here a piece of mass I can see the force and the acceleration. If I were to double the force, then the mass will disappear. That's how scientists communicate, and I don't have the time, but I'll show you. I can prove it in analyzing the kind of exercise high school algebra is being taught. So we are replacing the old oracle with a new one. I call it data generating models. It's not a new object because physicists use it, because economists use it, because even all those that are using structural equation models are using, they don't know what they're using. But it is a data generating model. It's different than the joint probability. I mean, many economists will vow that the economic model is nothing else but a parsimonious description of a set of probability distribution. So it's nothing else, it's just a set of probability distribution. But that is not what it is. It is really a data generating model which tells you an invariant strategy by which nature assigns values, not probability, values to variables in the analysis. The price has a certain value. The object has a certain temperature. This object has a certain pressure. The room has a certain pressure. Somebody takes care of deciding what value all these variables should have. And this is, let me show you how I perceive of that complex factory of values that we call reality or nature. We have to give it a formal description, or else we wouldn't be able to continue with the exercise. So it's a painful decrowning of a beloved oracle. Very painful. And this is what we want the oracle to do for us, to answer evidential problems, which is easy, that's statistics, action questions, what if we do double the price, what if we ban cigarettes, counterfactual, what if we did things differently, and that's very important because that is the source of should be the source of machine learning. Okay. Going from failure into analysis of your own software, that's called the ego, okay, and see what sub-strategy in my model of myself is responsible for the failure. We have names for those questions. What is, what if, and why, and lo and behold, they form a hierarchy. Hierarchy in the sense that there is a very little leakage between these layers. It means that you cannot get an answer to a query in level I unless you have assumptions of level I or higher. So you cannot answer a question of policy, what if I do something, unless you have someplace in the assumption set an assumption in that layer. That is a proof. Okay? It's not something that I dream. So you have a syntactic distinction between them. In the middle layer we have a do A, P of y given do A, and then for the question why we have a counterfactual. P of y had A been, I can't read it, but some value, given that I actually observe something. Like I know that I observe failure, what if I've done things differently? Well, analogy is Plato cave. Statistics is what these scientists are trying to figure out when they watch the wall. The wall is full of shadows of objects which have three-dimensional character in the real world, and we are watching the shadows on the wall and trying to build an understanding, trying to build a building for data analysis. That means building the shadows, the calculus of those shadows. Okay? The calculus could be simplified a lot if you just imagine that they come from reality, namely three-dimensional object. That's why I advocate a building for reality science, not for data science. Okay. There's a very simple dichotomy between associational concepts and causal concepts. It's so simple that every high school kid should know what it is. And the definition goes like that. Every concept that can be defined in terms of joint probability, density function, or joint probability of observed variable, it's associational. It's statistical, I should say traditionally statistical. And every concept that cannot be defined in terms of joint probability of observed variables, I'm going to call causal, for lack of a better word. I could have called it extra statistical, but I don't want to offend anyone, so I'll call it causal because I would like statistics to embrace the branch of causality. So if you look at the left, you see the kind of concepts that we've been using a lot among ourselves in the laboratory as well in the textbooks, okay? Some of them look very familiar, and they were never received, even the title causal. Like, for instance, take confounding. It took years for epidemiologists to figure out that confounding, the concept that we are fighting constantly, is non-statistical, can never be defined in terms of a joint probability of the observed variables. Take, for instance, the idea of randomization. It appears in many statistic textbooks, right? That randomization is obviously a statistical concept. It is not. You cannot define randomization in terms of joint probability. For instance, I give you bivariate joint distribution of x and y. I tell you that one of them, either x or y, is randomized. Can you tell me which? No way. Okay. You just look at the Gaussian distribution, and it doesn't tell you who is randomized. Okay. So you cannot answer the question about randomization. You cannot define it in terms of joint probability of observed variables. You have to postulate all kinds of things until you talk about randomization. It wasn't done by Fisher. Fisher did not do that. He relied on our intuition. But you know what randomization means. You go take 5,000 people from the pool. Well, 1,000 of them go to the control room. Other goes to the treatment room. And then what do? Then you force people in the treatment room to behave differently than they would have acted otherwise. Thou shalt smoke 2 packs a day, right? Whether you want it or not, because this is the procedure called, the protocol of the experiment called for that, okay? So you have an intervention. You cannot have randomization without intervention, and therefore it belongs to that side. Effect, explanation, right? Ignorability, exogeneity. I mean, you can laugh today when you look at the literature on exogeneity in economics textbook. A whole bunch of literature. What is exogenous? What is exogenous? They tried to explain it in terms of joint probabilities. It doesn't work. It's here. And it helps you so much to understand this dichotomy. Well, how does it help you? Every time I read a paper, I review a paper, and it says the word effect, for instance, I know that there is always some causal assumption someplace. So I'm looking for the causal assumption. If it's not there, I reject the paper. Because it has to rely, any one of those, it relies on causal assumption. And you can even tell what layer of the hierarchy the assumption should be. Okay, so now once we agree that we have a very clear dichotomy, like oil and water, then the question comes, how do you get a causal conclusion? Okay? No causes in, no causes out. You cannot get a conclusion which has a causal character unless you have causal assumptions there. Previously, we had data coming to conclusions. The conclusions were associational. Now we are in the whole paradigm. It's a mixture. The input is a mixture of causal assumptions and data. 2 questions comes there. Where do I get the causal assumption? Causal assumptions. We live in a world in which people talk causally. So I get it from my teachers, I get it from my textbooks, I get it from science, I get it from experiments that other people conducted. This is all accumulated. This is what we mean by knowledge, science. So we get it either from science or from experiments that I can conduct or other people have conducted. Okay. Where do I get the data? From the big data industry. It's available, right? That's no problem. But remember that you cannot get anything done in the causal dimension without causal assumptions. So suppose I'm an enlightened statistician. I'm willing to accept causal assumptions, and I can, without testing them, that I'm going to incorporate them in my study. The question comes, how do I express them? By definition, you cannot express them in the language of probability. Once you express them, then they will move into the associational side. But we said everything which is causal cannot be expressed in terms of properties of a joint distribution. So how can you express the assumption that you are willing to embrace? Causal assumption cannot be expressed in the mathematical language of standard statistics in joint probability. So you need a new language. This is the next hurdle that is, I call it a mental barrier. People will go to war on languages. They will agree on principles. He's one God and loves your neighbor and all this business. So good. But what language you express it? I'll go to war. And that we have a war today. How do you teach undergraduate statistics or even computer science? How do you teach them to incorporate causal assumptions when you need a new language? If they cannot be expressed with a beloved Bayesian conditioning bar. Statisticians were not helpless. They invented such languages. The first was Cyril White, a geneticist. He expressed them in structural equations with diagrams. Recently, Neyman and Rubin invented the subscript notation for potential outcome. The value of y had x been small x, had the temperature being 31 degrees. And in philosophy, about the same time, this conditioning operator was invented, expressed that way, okay? Y had x been small x. Okay, forward. This is the oracle, the new oracle. Collection of functions. The way you and I talked physics, F is equal to ma, but many of them. So this is, forget about all the rest. This is just done to defend myself against criticism. This is the working horse. Every variable gets its value depending on what other variables in the domains are, plus I separate the other variables in two parts, background variables, for which don't ask for explanation. They're bare, okay? It's a political climate. Or the climate, the weather, over which I have no control. I don't worry about the explanation. A meteorologist would worry, but I don't. So these are designated as background variables. They have no functions in the model which determines them. And then I have a collection of functions. If I want to play the game of uncertainty, these are all deterministic functions. Uncertainty comes from ignorance about the boundary conditions. Yeah.
Is there a connection between fuzzy probability and fuzzy statistics and what we're doing?
I don't want to go into fuzzy, but this is indeed an assumption. This is a Laplacian view of nature, okay, which means the probabilities and uncertainties evolve only because of our ignorance of the boundary conditions. Okay, it is not inherent part of nature, like Heisenberg uncertainty principle. It excludes the Heisenberg uncertainty. It's classical physics. Okay. So if you assume joint probability on the background variable, it induces, because of the deterministic nature of these functions, it induces probabilities all over the endogenous variables, and the rest is computable. So from what can I do with it? Here's an example. Okay, structural equation. Y is equal to beta alpha plus beta s plus u. Who hasn't seen an equation like that? Everybody has seen it. If you took economic 101, you took physics 101. It's over there. It's not regression. It says that nature, before deciding on the value of y, nature goes and asks x, hey, what's your value? Are there any factors, other factors which affect y? What's your value? I'll add alpha to it, and I'll determine the temperature of this object will be 31 degrees. That is a view of nature. And it's giving face to nature, which doesn't appear in any statistic textbook. I checked recently of all the regression textbooks in statistics. None of them give face to reality. All of them say, but remember, correlation is not causation. What we really want to know is the effect of government policy on the number of accidents, driving accidents. Okay? But this is not. What you get is only prediction. They never ask and never give the students, what do we really want? Okay. Regression is not what we want. What do we really want? Now give me equations for what? Give me a formal description of what we really want, of the true. Some of them go as far as saying, but this is not the true regression coefficient. You have a regression coefficient that you estimate, fine, but it's not a true one. The true one has a different name, but you don't have any equations. A mathematical description, a formal description. And that is what I feel today is the hurdle. It will take another 17 and a half years, I assume, to get the reality, a face of reality into regression textbooks. Interesting. Economists have it. All the equations are not regression equations, but structural equations. Psychologists have it. Social scientists have it. Okay? But they don't know what they have. They think that they have regression, or at least they apologize every time it's not regression. So it will take another 7.5 years. I think they will be ahead of statistics. Economists, epidemiologists already are in believers. They have totally changed their textbooks. Okay, next. Here are the two basic laws of causal inference. This is the first one. Counterfactuals are easily computed from the oracle, which is a structured equation. Give me that structural model, which I call M, structural causal model, collection of equations. The potential outcome, y sub x of u, for unit u, unit means individual, name u, or it's individual with characteristic u, is equal to the solution of y in a mutilated model m sub x, in which the equation for x is replaced by a constant. Variable x equal to value small x. So here you have schematics. This is your model of reality. Okay. That's how things behave normally. Okay. Every value gets a value. X looks at u and decides its value. Y looks at u and y decides its value. Now you want to predict the effect of intervention. What if x was 31 degrees? Intervention means to disable the influences that previously determined the value of x, and it was u, and force yourself upon that variable with your muscles and your will, and thou shalt be 31 degrees centigrade. Okay? Thou shalt not smoke. Okay? No more is U affecting X, so you have a new model. It's very simple. It's almost embarrassingly simple. Calculate the solution in this mutilated model. What you have is what people call potential outcome or result of intervention. There's nothing more to it. I can just summarize it in a fancy name, fundamental equation of counterfactual and so on, and frame it in a square, in a rectangular, and put a definition here and play the role of a game. It's a high school algebra. I'm embarrassed even to call it. Unfortunately, no one is using that. I'm not saying you're not. The enlightened people do. But I'm talking about ordinary people, that even those that vow for potential outcome. Okay? They don't realize that potential outcome are nothing else but abbreviation of structural equations, our understanding of reality. So this is the first thing. You want to really compute counterfactual, describe the world in terms of collection of springs, and the answer is there for you. High school algebra. You want effect of intervention? I just did the whole thing. I replicated here because intervention is nothing else but summary of a counterfactual. So the effect of intervening and setting a variable to x, its probabilistic effect on the outcome y is given by the probability of y under such mutilated model. If you know the probability for u, you can compute, this is a constant, compute the probability for y. High school algebra. Okay. Now we go to, okay, the second. I want to introduce the second principle of causal inference. You had already one. The second one is, how do we compute now the probability of y? Okay, I told you high school algebra, now I have to prove it. Okay. So if in the original model you have a probability distribution on x, y, and u, as done here, if you break it down into a chain rule in the order of causation, what will be the probability on the outcome y if I were to intervene and set x to small x? We know what it should be. It should be the probability of y in the mutilated model. So I have to remove that link that connects from u to x. Strike out this factor. Okay. Next, I write it down. What I have left, the probability of y and u, given that I do x, is the product of just two factors, not three. Easy. Right? But I don't want u. I wanted the probability on y. So I marginalize over u. That's not hard. And look what we got. The famous adjustment formula, right? You adjust for u. That's exactly what you do when you want to adjust for something, which Fisher call allow for variations on u. So if you observe u, no problem. You have a formula for the world after intervention. You adjust for other factors that affect y. Okay. What if you don't observe all the confounders? If you don't know them, or if they are measured, but if some of them are measured and some are not. So I'll go now, for that we have a calculus. But built on what? We have to have syntactic machinery that allows you to predict the causal effect of x and y when some of the u's are not available. So you cannot just plug in these probabilities and sum over u. Here comes the second principle of, I don't know if I need it, but just to enforce my previous statement that counterfactuals are easily computable for structural equation. I'll give you an example. Assuming that you have this treatment and study time and score in educational experiments, this is what the graph stands for, collection of these equations. Okay? The score on an exam depends on two variables. The kind of treatment you get, kind of educational program you're in, and the amount of time you spend on homework. Okay? Plus epsilon. Epsilon is very important. These are the U factors. These are the differences between individuals. Okay? To explain the differences. Okay? Now, I want to ask an ambitious question on that exercise. First, I pass it through, excuse me, this should be alpha, beta, and gamma. So I pass it through a routine of estimation, and I get the coefficient from the population. But I'm after asking a very hard question. A student named Joe measured a score of 0.5. He spent 1 hour a week on homework, and he got a score on the exam of 1.9. Listen to the question. What would Joe's score be had he doubled his study time? Counterfactual. On specific individual. Okay. Something you don't see in the homework of chapter 1 of structural equation models or economics. Very simple question. Most economic professors will fail on that. I can guarantee you that. I tried it in many universities. It's high school algebra. All it asks for you to do is to interpret counterfactual as a mutilation on the model. So let me mutilate. Had Joe doubled his study time. Study time was previously determined by the program, by the teacher. Now I'm going to mutilate it, and I say, forget about that. No more is the study time enslaved to the teacher. Now it is set to double what it was before, and it's going to receive the value 2. I have a new set of equations. Look, 1, 2, and 3. I can solve it. All the coefficients remain the same. I've only mutilated one of them, beta. All the rest remain the same. I can solve for y. Here it is, 2.3. So I answered it. Okay. So you see, I promised you a high school algebra exercise, and it is. It's something that 90% of economics professors do not know how to solve. And I'm it's on a video now. Okay? I would like it to be recorded. Because the ramifications of that are so far-reaching. Here it is, the confusion of a century. Okay, the confusion between regression models and structural models. The first is claimless, non-falsifiable, the best linear estimate of y given observation on x. And the second one is about nature. It's the definition of a structural equation. Look what they say here about B. Okay? B is defined in terms of an operator, do. So B is just the partial derivative of the expected value of y, given that we do x, and we do x equal to x1, x2, we take the partial derivative. Nothing else. And in that case, x need not be orthogonal to the residual. It's not a residual. U doesn't stand for the residual after the analysis. U stands for the omitted factors. Totally different and totally confused in the textbooks. We just finished a survey of 6 influential textbooks on structural equation in economics. None of them has this distinction. They all know it, by the way. You cannot talk to these professors because they know intuitively. And they're true, they will not make a mistake. But poor students have to go through that without the help of mathematics. Okay. So one is analyst designed, the other one is nature's designed. And here are the assumptions. Whenever you put down a structural equation, you make assumptions as you wouldn't make if you did regression. Here are the assumptions about the y is equal to bx plus ui, right here. Okay, before you put it, you have to be careful, because you are expressing your view of nature. So what do you assume about nature? First, linearity. Right? If you go from x equal to 20 to 21, you'll have the same effect as if you go from 30 to 31. That's linearity. And here is that z does not appear in this equation. What does it mean? It means that nature does not need to consult z before deciding on y, once nature consults x. So that is called exclusion restriction. All economists make it. Right? But what precisely is the reasoning process by which you come out with that remains unclear. So what remains to ask, of course, the mother of all questions, when would be something we can easily compute, be equal to A is easily computable by regression, but what about B? For that we need some calculus. So in normal regression textbooks, you'll find that conditions that guarantee that B is equal to A. Okay? If the omitted factors are orthogonal to the regressor, fine. But how do I know that they are orthogonal? How do I tell that from the model I have? Normally it's being taken as an assumption. If you assume that, then you're done. Do you know what it takes to verify your mind? Because you are in a process now of putting down equations, right, and deciding what procedure. You know what it takes to decide if this is true? This is something that the textbook tells you as a condition. If this holds, then B is equal to A. But how do I tell? If my picture of nature, I'm talking as a computer science now, you have to decide what you do according to your formulation, formal description of reality, which is a collection of functions like that. How do you decide when this holds? Okay. Well, that requires the second law of causal inference, which I'm giving you right now. I'm doing on time. Probably I exceeded my time and never get to the applications. Anyhow, so here it is. Bing. I'm repeating myself. This is the second law. You give me the graph, which is a blueprint for your equations, for the structural model, and I can tell you that a certain conditional independence should hold in your distribution, the one you are measuring, okay, just by looking at the structure of the graph. It's called disseparation, but the idea is very powerful. I mean, I don't have to go through the axioms of conditional probability to do this exercise. I can just look at the graph and tell you, here's an example. This is your model of the world among variables, 4 variables: sprinkler, wetness, rain, and climate. This is how the structural equation will move. I put it in the form of a graph because economists would not allow me to put a graph in their textbook. The Coles commissions were very careful mathematicians. They didn't allow any gimmick like graph from Symbolic, right? That's how they work. You give me that, that's my model. Now I'm going to infer things about what I observe. Now, assuming that you observe C, or you observe the condition, the joint probability on C, S, W, and R. What can I tell about this joint probability? Well, this gracious gift of nature tells me that no matter how complex those functions are, look at them, I didn't determine their nature. They could be hyperbolic arctangent of something, or they could be discrete. And there's a complex process between climate and sprinkler. And it involves feedbacks, and it involves other U's that are impinging on that. No matter how complex this process, I know that this linkage is a summary abstraction of millions of microprocessors. And still, I can tell you something about the joint probability of the 4 variables. I can tell you that, like a gift of God, I said, that independent on F's and P of U, I can read from the graph and certain constraints. And here they are. Every time there is a separation in the graph, namely a missing link, then there is a conditional independence attached, claim imposed on it. Like here there's a missing link between C and W. And I can tell you C and W ought to be independent in your observed distribution once you know S and R, because S and R are the separators between the two. So you go over every missing link dictates a certain constraints. This is also a missing link. So I have this condition. Why didn't I say a condition on C and W? Because of a little twist there. It has to do with colliders. I don't want to go into it. Colliders act differently than a fork. Okay. Let's skip this twist and just imagine that a graph conveys a set of assumptions about the distributions, imposition of certain constraints. Application of that, look how many applications I can now get. Number one, I can submit my model for testing. If my model is wrong of reality, the model dictates a certain claims. It dictates a certain constraint on distribution. If one of them does not hold, then my model is wrong. And I know which one. I know who to blame in the model. It's two important things. Okay? And the other one is structure learn. I can play the game of I don't know anything about reality. But let's look at the conditional dependencies in my data. They dictate certain substructures in the graph. I can perhaps put them all together, and that's what we have in structural learning, put them all together and say perhaps the totality of them dictate a certain directionality between X and Y, so I know a direction of causality. Perhaps they don't, but I can find a parsimonious representation for the sum total of all the constraints. And that's what we have in causal discovery. But let's go one more step, more modest. Assuming that I start with knowledge about the graph structure, what can I do with it? I can answer what if do question. What if I do kind of questions, and I reduce it to symbolic calculus. Symbolic calculus is elegant for computer scientists, and it comes from the fact that computer scientists are lazy. They want to deliver intellectual tasks to machines, or to a grammar, to compute for them what they are too lazy to think about. And the same thing goes for reducing scientific questions to symbolic calculus. I'll show you some example, and now I'm entering the application era. How much time do I have so I know how to?
So it's been 1 hour.
1 more hour? Thank you. Okay, so now we got to the two principles. This is how the calculus go. It's all derived from the two principles. Assuming that you have a sentence which contains a mixture of do and observation, actions and observations. Yeah. You can convert it to another sentence, also containing action and observation, if you consult the graph and you get a license. Okay. So you have three rules here of manipulating sentences which are a mixture of actions and observation. And if you are in the business of deciding identification, for instance, or you decide what you want the outcome to be. By applying those rules sequentially, if you get the answer, then you know it is valid. To show you an example, it's complete, by the way. So we haven't forgotten any rule. Okay, here's an example. I have smoking It appears in my book, so it's nothing new. I just want to put it in this context. Assuming that your perception of the process that lead to cancer from smoking is that you have accumulation of tar in the lungs, and that's what actually causes the cancer, and you have a confounder. You have some sort of a genetic trait or something that makes people crave for nicotine, at the same time put them in the high cancer risk. Okay, that's a Fisher's excuse for smoking. Okay, so the complex model, if you think about it, we have a confounder and we cannot, it's unmeasured. And can we get the effect of smoking on cancer? Well, first thing, before you start, you have to put down a formal description of your question. It's the hardest thing that I found, because people did not have a formal language to express the real question, the real research question. No. Until now, I'm on the board of editors of the Journal for Causal Reasoning or Causal Inference. We reject papers one after the other because people did not define, authors do not define their research question. They start saying, I'm using, I'm applying, I do. What is your research question? Well, your research question is, what would be the probability of cancer given that I do something to smoking? Either I ban cigarette or I force people to smoke. Okay, I do S. Once you define the question, everything follows from logic. You don't have to think anymore. This is your assumptions, are all embedded here. They give you the licenses to go step by step. Zoop. Okay, and what do you want? I want to infer that from observational data. Just passive observation. No intervention, no experiment. I just watch P of X, Y, and Z, or P of S, T, and R. That's what I get. I can estimate those. If I succeed in removing all these purple terms from my initial expression, then I'm done. In this sequence of rules allows you to remove the red do operators, and you end up with an all-white expression. That means that you have reduced your causally inspired question to something you can estimate from observational studies. Okay? No intervention, and it means it is identified. Okay? The causal query is identified from what? From a combination of data. Here, look at it, the data, okay, conditional probability, and the assumptions. Let's not forget that. They're all in the graph. Here they are. They give you a license to go from one step to another. Bing, 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 bing. So they're all in the graph. For instance, one assumption is that the tar is only listening to smoking, is not listening to the genotype. The amount of tar accumulated for a given amount of smoking is not depend on the genotype. Okay? That's an assumption, missing link. Okay? There's a missing link between smoking and cancer, which means everything goes through the tar. These are the assumptions embedded here, but the nice thing is they're embedded in a language that I don't have to explicate them syntactically. I can just look at the graph. Okay? In the language in which we communicate, in the language in which we describe nature. So I go through that, zoop, all white, identified, estimate dot, you go. That's identification, and that is the exercise that I describe as policy making. Here's another exercise. What's the effect of warm-up, I say exercise, warm-up exercise on injury in sports medicine? Okay. It was taken from a paper by Schreier and Platt. They're working in sports medicine. Okay. And here you have many variables. Some of them are easily to measure, easily measurable. Others are multivariate and requires a lot of effort, maybe cost to measure them. Which one should you measure if you want the effect of warm-up on injury? Okay. And this is a real problem. This is a problem of the many generation of epidemiologists have dealt with, and I think generation of statisticians too, and social scientists, and everybody. You have, one thing is different now. You expressed what you know about your field of expertise in a graphical form. Okay. The way that you and your colleagues communicate in the cafeteria, and the way that allows your colleague to critique your model. Say, how come you don't have a line between genetics and previous injury? Okay. You can discuss it in the cafeteria because it's clear to everybody. Okay. So you have a clear and transparent model on which you impose your question. What is the causal effect of warm-up on injury? Okay. The answer is now we have reduced the causal calculus to a graphical condition. Give me a graph, and I can demonstrate to you what you should measure and what will give you bias, and what you should take into account, what you shouldn't adjust for, and whether you can go beyond adjustment. For instance, this is fine. If you measure the parents of the outcome, you're done. Or the parents of the income. Okay. This is called the door condition. Okay. For example, even that is okay. Okay. Here you're measuring and you pseudo-adjust for an intermediate node that is on the path between the causal variable and the outcome. If you measure these two, you're done. Because it may be the tissue weakness is very hard to measure. And anything else you want to ask? For instance, thou shalt not adjust for previous injury because it is a collider here and will cause you bias. And you can do it for average treatment effect. You can do it for ETT, effect of treatment on the treated. You can do it for probability of necessary causation, which means if you know the injury and you know the guy took a warm-up, what would be his injury rate had he not been subject to warm-up, okay, for a specific guy? So the question is solved. I can move to the next one unless you have some questions. I'll stop here and say, do you have any question, any doubt whatsoever that the problem of policy analysis is solved? I purposely use provocative statements to evoke from you questions. And what about if I? And what about if I want to? Well, keep on, poke me. Yeah.
So here you have a graph.
Yeah.
My question is not criticizing you. I am asking you to estimate the probability. Are you allowed to repeat conditionally the experiment? Because you want to estimate the probability, you want to test whether or not.
I want to compute the probability of a hypothetical experiment by which I subject the team to 2 hours per day warm-up exercise.
And you have many, so you
I have a record. I have the data.
Yeah, but you have the law of large numbers to help you estimate the conditional probability.
Sure, that's all. I have a joint probability of the observed data. I do have a joint probability of all the variables that are here. Okay, I'm not dealing with estimation. I'm doing with identification. Okay, I have infinite samples of them.
Has estimation been developed in this context? Has estimation been developed in this context?
Yes. The propensity score analysis is a powerful estimator, and Mark van der Laan is doing a target-specific estimation technique, which geared to this kind of questions. Yeah, but first step is identification. Assuming that you have infinite samples, can you get the answer? And I admit, I insert a lot of assumptions in this graph. Okay. Is a missing link from there to there? All these are debatable, are discussable. Fine. They are there, but they are qualitative. You see, they're not numerical. They're qualitative. It's something that your peers can point out to you and say, have you considered the possibility that there is a genetic influence between genetics and work and warm-up, or some other connection that is not in the graph. The assumptions in the graph are in the missing link, not in the link. The link said there is some causal relation between the two. I cannot commit myself to any. I don't know the form of the functions. I don't know the distributions of the errors. All I know is qualitatively what I perceive to be the workings of nature, of reality. And from that, I can answer very powerful questions. Okay, so we all agree that policy analysis is to solve problems. Here I summarize it mathematically. The estimability of any expression in this form, I would like to help you to read this expression. It means that here you have a collection of outcomes, y1 up to yn. I have a collection of actions, do x1, do x2, do xn. Imagine that you have a time series and you can take action at different time period. You can prescribe a treatment for a patient which is being monitored over 10 years. Okay? So you say after 5 years, if he doesn't do what he needs, if he doesn't behave like he ought to, then I will increase the dose by 5%, and so on. So the plan is good over time. That's why we have here many actions. And these are the observations which are taken over time. Okay? So any expression of that kind is decidable in polynomial time. What does it mean decidable? I mean, I can decide whether it can or cannot be estimated from a joint distribution of all these variables. And I can, if it is decidable, then I can produce the estimand in polynomial time. I can produce an expression like the white one that you saw here below, okay, which is the infinite sample behavior of that expression. The estimand. Estimand is a functional over a joint distribution. That's something that you ought to strive to estimate with a finite sample, because it only gives you what the infinite sample is. And it's complete, which means you cannot do better. I mean, you can read the literature, but I did this experiments with this exercise with a different kind of trick. Your trick must be equivalent to my trick, because this is complete in the sense that if the first step tells you undoable, I applied all the rules of the calculus and I failed, or the graph tells me failure, then I know it's not going to be estimable by any method, no matter how smart. And that's important. You need to know when you fail. If you have 4 equations and 5 variables, 5 unknown, the answer is undoable. Okay? It will save you thousands of man-year labor. Forget about the references. We're not dealing with history now. I just summarize the process by which every exercise in causal analysis goes through. I look at it as an engine, an inference engine, from computer science viewpoint. You have input when you desire certain outputs. That's all there is. And the rest is just grinding through the machinery. Okay. What are the input? Here are the inputs. A causal model, these are the assumptions. Either in a graph form or in syntactic form, doesn't matter, but you have to have a set of assumptions. Because we agree that no garbage in, garbage out, no assumptions in, no causal conclusions. And you set a query of interest. I want the effect of smoking on cancer. Express it. Sometimes it's very complex. I want the effect of smoking on cancer for those people whose father is a lawyer and who has taken 2 cigarettes a day. What will be the reaction, the cancer risk, had they been banned from smoking? So that is a kind of compressed questions expressed in counterfactual language. Okay? And then you have data. That's easy. That's free today. Now you go through the logical analysis. What can you get out of it? Well, you have three types of output. All the logical implications of the model without even seeing the data. You can tell which data is identifiable or which query is identifiable, and you can talk about testing the model testing here, which come from the testable implication of your model, which are displayed to you in the form of this operation dictates. So it's a scientific process, Bing. Now I come to a question about what language is preferred to express your assumption. Because still in 21st century, we have good papers written where the model assumptions are not expressed in a graph form, but expressed in symbolic form. So let me show you the trade-off in graphical form and symbolic form. I'm going back to the...
Can you pick up the microphone? It's rubbing against the counter.
It's rubbing against that, yeah. Oh, it's even... Aha. Can you hear me? Okay. I'm going to talk now about the trade-off. This is the old story we had about the causal and the smoking and the tar and the genotype here. I express it to you in English. Okay. And I can express it in English to a professional to understand what I mean. I just accompany it with a graph because it helps as a mnemonic device. Nothing formal about it. Now, there is a language called counterfactual. I just defined it for you. Abbreviated structural equation. And this language is used by many statisticians. It's called potential outcome. Because z sub x means the potential outcome of z had x being small x. Okay. In this language, it is, by the way, equivalent to structural equation. You can express all the assumptions. And this is equivalent to what we said upstairs in English. For instance, let's look at that, for instance. It tells you that z, y, had z been small z, is equal to y, had z been small z, and x did something, which means there's no direct link between x and y. So missing link can be expressed in counterfactual terms, like here. See? Doing something to x will not change y once you decide what z is. But it's all written in the language of subscript and not in terms of Bayesian conditionalization, because it has to do with counterfactuals. Okay. So you can express all the assumptions which are in the graph in syntactic form. I'm removing now the graph. I'm leaving you with the syntactic form on purpose, because I want to expose you to the predicament that people who are using syntactic form find themselves. Okay. What can you tell from those? Here are the kind of things that are important. Are they consistent? Can you tell if one of them doesn't refute the other? Very hard. Okay. Can you tell, for instance, if they're complete? Namely, if you haven't forgotten any? Perhaps, you should add to it some other counterfactual equations to complete your perception of nature. Can you tell, for instance, if they are redundant? Perhaps one of them implies the other. Can you tell, for instance, if they are plausible? I put back the graph here, because now you can tell if they're plausible. But when you have the syntactic form only, how can you convince your friend in the cafeteria that these are plausible description of you and I understand about the effect of smoking on cancer? And the last one, are they testable? You look at this collection and say, are they testable? And you don't have the answer. So these are the factors that makes me prefer that, which is equivalent, by the way, logically equivalent. Every theorem in one language is a theorem in the other language. But look how clear this is. It stands for nothing else but the structural equation here. There is a function f3 which determines the value of y given that you know z and u. Plus there is a missing factor, a noise factor, which comes from omitted factors, which I did not put in the equation. Okay? And I assume that the epsilons are independent on each other. It's exactly what is assumed here with this independent. But look how clear this is, how transparent it is. And I can now operate on that and get all the answers that I need. Okay, so it summarizes with a symbiotic. I summarize it with a symbiosis analysis, which I recommend. Express your theoretical assumptions in structural language. Express the query in counterfactual language. Translate one to the other and use whichever is good for you to get the answer to your questions. Now I want to talk about mediation. It's a very hot subject because it was recently been supported with software. And if you have people invest in software, and you know it's the next 10 years is going to be popular among workers in the field. Mediation. We are interested not only in the effect of cancer, effect of smoking on cancer, but how it goes about, what goes in between. So we have to distinguish here between direct cause and indirect cause and quantify the degree of influence that goes through any path, any suggested path between X and Y. First problem we face is the definition. It's a problem because even great statisticians like Cochrane and Fisher failed on that. And no wonder they failed. They didn't have a language to express it. They should have had a graph language, they should have had counterfactual. They didn't. All they had is poor Bayesian conditionalization. So they had to express their ideas about direct and indirect cause using this primitive language of conditionalization. They goofed. They did by analysis of variance. Even Don Rubin, in his Fisher paper, pointed out that Fisher was wrong. And we can forgive Fisher because he didn't have the language of counterfactual or the language of graph. We cannot forgive people who are today, with the availability of these two languages, are still doing Bayesian conditionalization to define direct and indirect effects. I'll discuss this issue and give you some examples of why it's important. Now, when we talk about direct and indirect effects, they have policy implications, but concerning different kinds of intervention. So far, we talked about intervention to be the act of fixing a variable to a certain constant. Raise taxes, make me laugh, okay? Double the price. That was the kind of actions. And now we're talking about different kind of action. For instance, eliminate disparity in hiring, or eliminate disparity in education, gender disparity in education. Okay? And people make this kind of decision because you have to decide if you want to invest $1 million in education or $1 million in penalties on employers that discriminate in hiring. Here's an example. Gender. What's the direct effect of gender on hiring? As opposed to that effect which comes through disparity in training and makes women or other minority group less qualified for hiring. It's important to distinguish between these two paths, okay? Because they are curable by different means. And because they are curable by different means, it means that you have to make decision of where to invest your available resources. So how do we define? We computer scientists understand that before you decide on this question, you have to formulate the question. You have to define what you mean by direct effect, define what you mean by indirect effect, and then go to the exercise of estimating the data. But first, define. Well, here's one definition. Okay. I fix qualification, and I'm looking at the effect of X on Y, gender on that. So I fix Z at some value. Maybe qualification is 12 years of college. Okay. Bing, I fix it, and I want to see now the expected value of hiring if I force the gender to be something. And excuse me for using a do on a variable such as gender. Okay. Formally, it doesn't matter. Because the do is a symbolic operation on the graph, on the model, and not on physics of gender determination. So assuming that I have treatment 1 or treatment 2, I want to see the difference. If I fix the intermediate variable z to some constant, this is called the control direct effect. Okay? It's z dependent. If I fix it to z equal to 0 or z equal to 20, I get a different answer because there is interaction here. And this is solved because of result number 1 that we had on the previous slide, that every expression involves doing and seeing is solved problem. I can tell you if it's identifiable or not, give me the graph, and I can tell you how it is to be estimated once it is identifiable. So it's a solved problem. Here I'm warning people, I don't have to warn you because you listen to me for a whole hour, that thou shalt not condition on z. Thou should use z under the do operator. Okay? This is the official fail. Okay? And this is something that people have a very hard time, even people who spend their whole career on mediation. Okay? I have a very hard time liberating themselves from the habit of conditioning on z. Well, you want to keep z constant. Well, I want to keep z constant. We say, what's the effect of x and y? How do we define the direct effect? If we keep the intermediate effect constant, we forbid it from changing. Then whatever we observe must be attributable to x. Right? You and I understand it. It's true. But how do you fix? You fix z either by physical fixing, physical intervention, you hold it constant, or, which is a habit, which is a bad habit, you condition on z. We have a century of habit developed. If you want to fix something, you condition on it. Okay? So which means you look at only samples which has z is equal to 5 years of college. You eliminate all other samples and you look at all samples that satisfy z is equal to constant. This is a different operation altogether than physically fixing. And gives you different results. But it takes dislodging the habit, which is very hard. So help me talk to your social scientist. Yeah, go ahead.
Yes, I find it hard to understand the difference between...
Really?
Yeah.
So let's go to exercise. I really appreciate this question. Do you find it hard? Also, why didn't you poke me with the question? Why did you wait for this gentleman to gather the courage and say, I don't believe it? If I select only samples for which z is equal to 3, it's the same thing as fixing z to 3. Right? Okay, so let's look at the exercise. I need a board here. I'm sorry, I didn't mean to insult you. But I found it so valuable that someone asked the question. Oh, can we temporarily lift this? No, I can do it here. I can do it here. X, can you see that? Z and Y. Assuming that we don't have this arrow, but we have a latent variable here that's fixed like that. What is the direct effect of X and Y? Intuitively. Zero. Okay? Because whatever variation of Y you have, they come from variations in L, in latent variable, not from X. Okay? So the answer should be zero, right? Assume even that the equations are Z is equal to X plus Y plus L. No coefficients, no errors, deterministic. And Y is equal to Z, to L. Simple things? Okay? So this is nature. We know the answer ahead of time. The effect of X on Y should be zero. Now, let's do the exercise with two different schemes. In one of them, I condition on Z. The other one, I fix Z by physical force. Let's say to 0 or to 1 or 20, it doesn't matter, right? So let's first do the physical force. Physical force means that Z no longer listens to L. It listens to my force. So I have a mutilated model. See, this is something perhaps the reason why you don't see the difference. Because you are a victim of a century of ignoring reality. People do not tell you how to figure out what happens if I fix Z by physical force. Never! You don't see it in any textbook. Okay? All you see is conditioning, 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 right? No wonder you don't see a difference, because you haven't seen the reality. So here we have X. If you fix Z, which means Z listens only to your hand, to your muscles, Z is equal to 0. And then you have Y, and then you have L, and no longer here. This is what it means to fix Z physically to 0. What the answer is? The answer is Y is equal to L. Same thing. The answer is Y is equal to L. Yeah. Sorry, I don't have that. This is a mutilated model. Okay? I obey by the rule, or abide by the rule. So the correct answer will be if Z is forced to assume the value 0, Y will be the same as it is now, Y is equal to L. It will have some variations there, depending on the probability of L. But this is the answer. The correct answer, which means it's no longer dependent on X. X can vary widely, and Y would not listen to that. Which is exactly what the model of nature tells you. Y does not listen to X. Y listens only to L. Now let's see what happens if we condition. This is something we're all used to, right? Z is equal to a constant, so we have a model. Let's go ahead. I fix Z to 0. I condition Z on 0. In order for Z to be 0, we have to have X equal to minus L. How else would Z be 0? I mean, you allow X to vary, you allow L to vary, but you select only the samples for which Z is equal to 0. All the rest you throw away. You have many samples. Some of them have Z is equal to 0, some have Z is equal to 1. You throw away the 1s and minus 1, and you end up with only those for which Z is equal to 0. That's what conditioning means. So what happened for all these samples? They have a peculiar nature. That for them, x is equal to minus L. Correct? Let's compute y now. Y, according to our nature, says y is equal to L. So it's equal to minus x. Y is equal to minus x, which means you vary x and y will vary. Those of you who know the graphical model, how many of you know this operation? Only one. Oh, is this Columbia? Okay.
That's what we came to learn.
Oh, but if you don't poke your professors, they'll never teach you the real stuff. They keep on teaching you conditioning. Where would science be? Okay, so for those who know graphical models, you can just look at the, this is a latent variable, look at the graph, and you can see that thou shalt not condition on z because you form a collider. A collider gives you a spurious correlation between x and y, which is the result of this conditionalization. Does anybody have any doubt about the difference between physically fixing a variable and conditioning on this variable being constant? Ask me, please. I'm dying to ask to see where the mental barrier is. I'm walking like that as you see me here for 20 years. You can't believe how heavy the inertia is in academic circles for simple things like that. I'm talking to you seriously. You are in Columbia. You should appear in your professor's office tomorrow and bang on the table like that. Why don't we get 1 week in any statistics or economic 101 or any computer science are okay because they read other literature. But bang it and say there is a difference between the two. And the ramifications are enormous. The confusion is devastating. Yeah, we had a question. One of you had a question. No. Okay, good. Okay, so there's a big difference between the two. Good. Oh, it's good to talk in front of listening audience. Normally I talk in front of audience that know everything. And I don't get any questions. Anyhow, don't let this frustration of mine stand between you and me. Where are we? I need to have the advancer. I think I left it. Yeah, here. So here we now going to we had defined the control direct effect involving physical holding the intermediate variable constant, and he gives you an answer. It will give you a different answer depending on what value holds the constant. You can see that because if you have an AND gate here or OR gate, it will make a difference. And the next thing is to answer the question, can we get a number which is independent on z? Not because only it is convenient, but because we don't in reality hold qualification constant. We want to have an idea of what degree of discrimination is in hiring here, regardless of whether it is for low training people or high training. And this is the problem. You have two nonlinear functions, f and g, of unknown form. And you want to find they define the direct effect on x on y in a way that describes the reality of things. The reality is I'm going to let z be held constant in a natural way, which means every individual in the population who has a certain value z, training, okay, and you hold it constant, freeze it from the effect, from being influenced by x. That's what I mean by natural. Now, what is the effect of x on y? If you were to freeze the value of z for different value for every individual in the population. So here's the definition. It's expected change in y when we change x from some reference x0 to x1, and for each u we keep z constant, whatever value it attained before the change. So now you have a double counterfactual here. First, the value of the z would have been had x remain constant, and then you have a counterfactual between x and y. But we are not scared of counterfactuals because we know that they are just solving a bunch of equations in high school algebra. So we write it down. Here it is, a nested counterfactual. It turns out that in linear model, that definition will give you what you actually expect, beta, times the difference between x1 and x0. But in nonlinear model, it's going to give you a lot of insight about what direct effect and indirect effect means. Same thing we do now for the indirect effect. It's the effect, it's the expected change in y. Well, now we keep x constant. We just let z change. But to what value? The value that it would have attained had x changed. Had x be gotten from 0 to 1. Double counterfactual. And in linear model, you have the additivity property. Non-linear model, you don't expect additivity. Why should one be defined in terms of the other? It has a policy implication, as I explained before. Here is in terms of discrimination. Where should we invest our national resources? In eliminating disparity in qualification, in education, or in educating employer against discrimination. Okay. That is the trade-off, and we should do it before we see any data. And we should decide on that depending on the value of the direct effect versus indirect effect. Okay, so here's the solution. Once, if you assume a certain assumption about the structure of the model, about confounding, you get formulas estimand in terms of observable, in terms of estimable regression expressions, all conditional probability. You have something nice, which is a difference between the amount of response explained by mediation and the amount of response order to mediation. One is sufficient, the other one is necessary. The necessary says there would be no response but for variations in z, which is totally different than there would be a response explained by z alone. Even if you didn't have any direct effect, the indirect effect can explain what you observe. The difference between sufficient and necessary because of nonlinearity. So I go now to, we have a completeness result that tells you for any graph, I'll be able to tell you whether or not the indirect effect is identifiable. And I'll quit that for a second assumption, bing, bing. No, I'll quit that. It's just an acrobatic. Whenever I want to show off, I put down a bunch of graphs and show it. I can decide which one is identifiable and which one not, just to demonstrate, to dramatize the power that you get from this symbolic tool. So you give me a bunch of graphs, or give me a graph of arbitrary structure, and I can tell you whether the direct effect can be identified. Yes, 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 no, no, no. This is no according to the conventional assumptions, and this was yes according to the relaxed assumptions. Yeah. But that leaves us, that brings us to the next applications, which is important. Okay, I want to talk to you about it because this is another application that was in the blue sky list of many statisticians and many data analysts. The ability to generalize. I explained already what in the introduction. I'm going to elaborate it now. Here's a more formal definition of the problem. We want to understand under what conditions we can infer or estimate causal relationship learned from experiments to a different environment when experiments are not allowed to be conducted or cannot be conducted, or for some reason you don't feel like conducting it. So imagine that you have a laboratory, conduct experiments, you have a very clear idea of the causal effect of one variable or another. Now you go to a field. In the field you cannot conduct experiments, but things change. You know that you are making inference now about people, not about monkeys. About fighting in the battlefield, not about the simulation laboratory where you train helicopters, pilots. So this is an immense problem. It's philosophically unsolvable. How can you generalize from one environment to the other that you know it's different unless you tell me what is different? Let's quit that for a second. Here's the problem. Here's the laboratory, the field. If you assume that everything is the same, there's no problem. And it trivially, whatever you learn in the laboratory applies to the field. But what about if everything is different? He did experiments on amoebas. Can you generalize to human beings? All the variables, all the functions are different. And this is my trick of indicating suspicion that the functions are different. In the model you have one function, two functions, three functions, okay? I assume now that all the functions are different, so I put then a doubting square, an arrow. Beware, they could be different. Now this environment is totally different. It's a human being and it's an amoeba being. Nothing is transportable. So you have two extremes. One says, go ahead, apply it. The other one says, stay in bed. Don't make any claims, because nothing is doable. Well, science would not have progressed unless you can do something in between. You can generalize sometimes on certain characteristics and not others, and you should be aware of what is generalizable and what is not.